Good day, everyone. I would also like to express my warm greetings to my respected instructor, Engineer Juanito Rehenes. Good day, sir. I am Mary Therese Cartagenas from BSME 4A. Today, I will present and discuss an oral report about the exploration of fluid machineries. Our journey will encompass an understanding of these mechanical systems, their classifications, and their crucial roles in various industries. So first, I will introduce to you a brief information or introduction about fluid machineries and their application to various industries. Fluid machinery, also known as fluid handling machines, are mechanical devices designed to interact with fluids such as liquid or gas to perform various tasks. These machines are crucial components in the field of mechanical engineering, responsible for manipulating and controlling the flow of fluids for a wide range of industrial applications. Fluid machineries play a pivotal role in numerous industries, including but not limited to manufacturing, energy production, aerospace, HVAC, oil and gas industries. For manufacturing industry, they are used for transporting, pressurizing, and cooling fluids in manufacturing processes. For the energy production industry, in power plants, they are employed to convert energy between fluids and mechanical forms, as seen in turbines and pumps. For aerospace industry, fluid machineries are integral in propulsion systems, ensuring efficient airflow and fuel delivery in aircraft and spacecraft. Fourth application is to HVAC industry or heating, ventilation, and air conditioning industry. Fans, blowers, and air compressors are vital for climate control systems in buildings. Last application is the oil and gas industry, to which pumps and compressors are used extensively in oil refineries and natural gas processing facilities. The following shows the role of fluid machinery in transferring energy to fluids. First role is that it imparts kinetic energy. Using fans and blowers, it accelerates air to create airflow. Second role of fluid machinery is that it also increases pressure by pumps and compressors. The third role is that it extracts energy from turbines, converting it into mechanical or electrical energy. Fluid machineries can be categorized into 5 main types, each serving a specific purpose in fluid handling. The first type is fan or fans, if plural. Fans are mechanical devices designed to move air or gases. They create a flow of air by imparting kinetic energy to it, generating a low-pressure region behind the blades. They are commonly used for ventilation, cooling, and airflow in HVAC systems and industrial processes. Fan is also classified into 3 categories: axial, centrifugal, and mixed flow fans. These classifications cater to different airflow requirements, making fans suitable for applications like ventilation, cooling, and air circulation. So fan is classified based on their design and application. First is the axial fan. These fans move air parallel to the axis of rotation, making them suitable for high flow, low pressure applications like cooling systems. The right side of this slide presents the image of axial fan and its component. Second classification of fan is the centrifugal fan. These fans direct air radially outward from the impeller, generating higher pressure suitable for ventilation systems and air filtration. Just like axial fan, I have also presented an image of the components of centrifugal fan as shown in the right side of this presentation. Third classification is mixed flow fan. Combining features of both axial and centrifugal fans, mixed flow fans offer a balance between airflow and pressure. It is ideal for diverse applications. So, the basic components of fans include fan blades or impeller, hub, motor, housing or casing, inlet, and outlet. So, fan or blades, impeller, they are primary components responsible for moving air. The shape and angle determine the direction and velocity of the airflow, and the materials used for this vary depending on the application. Hub, it connects the hub is the function of this component is that it connects the fan blades to the shaft. It provides structural support and helps maintain the blade positions. Third component is motor. The motor provides the necessary mechanical energy to turn the fan blades. It can be electric or hydraulic depending on the application. Fourth is housing or casing. It encloses the fan assembly. It helps direct the airflow and prevents air leakage. Fifth are the inlet and outlet. Fans have designated inlet and outlet sections to control the airflow's path. The inlet is where the air enters and the outlet is where the air exits. Performance characteristics of a fan. First is the airflow rate. Fans are rated based on their airflow capacity, typically measured in cubic feet per minute or cubic meters per second. Second performance characteristic is the static pressure, which is generated by the fan. It is very crucial, especially in systems with resistance, such as ductwork or filters. Third performance characteristic is the operating point. Fans have specific operating points and their performance curves, where they achieve optimal efficiency. Deviating from these points can affect performance. Proper operation and maintenance of fans are essential to ensure efficient airflow, prevent breakdowns, and ensure the safety of personnel working with or around the equipment. So this slide shows the operation procedures for fans. First is the startup procedure. Startup procedure. For this procedure, we must ensure that the fan is securely mounted and all safety precautions are in place. Then turn on the fan motor and verify that it is running smoothly. Third is that gradually increase the fan speed to the desired level, allowing the system to stabilize. The second procedure is monitoring. Continuously monitor the fan's performance, including airflow speed and temperature. Then check for any unusual vibrations or noises, which could indicate issues with the fan or its components. Third procedure is the shutdown procedure. To shut down the fan, reduce the speed gradually to avoid sudden airflow disruptions. Turn off the fan motor and ensure it comes to a complete stop. Follow any specific shutdown procedures provided by the manufacturer. Fourth procedure is the regular maintenance. Implement a routine maintenance schedule to clean and inspect the fan blades, housing, and motor. Then lubricate moving parts as needed and replace worn out components as well. Keep the area around the fan clean to prevent obstructions. Safety precautions is the fifth operation procedure. Ensure that safety guards and protective measures are in place to prevent accidents or contact with moving parts. Then follow all safety guidelines and use personal protective equipment when working with fans. Sixth procedure is troubleshooting. If the fan exhibits abnormal behavior or performance issues, conduct a thorough inspection. Identify and address any problems promptly to avoid damage and maintain efficiency. Last procedure is the energy efficiency. We must also optimize fan operation by adjusting speed and airflow to match actual requirements. Using variable frequency drives or VFDs or other control systems can help save energy and reduce cost. The second fluid machinery classification next to fan is blower. Blowers are similar to fans but are more powerful and capable of generating higher pressures. They are used when a higher air pressure is required, such as in forced air combustion, pneumatic conveying, and aeration in wastewater treatment. Blower is also classified into two categories or classification. First is the centrifugal blower and second is the positive displacement blower. These classifications of blowers reflect their capability to generate varying air pressures, making them suitable for applications like forced air combustion and pneumatic conveying, as I've said earlier. So this one is the centrifugal blower. Second classification of blower is the positive displacement blower. The basic components of blowers are impeller, housing or casing, motor, and motor. These are the three main components of blowers. Impeller is the primary component responsible for air compression. It has blades that accelerate and pressurize the air. Housing or casing, it surrounds the impeller or rotors, guiding and channeling the airflow. The design of the casing, including inlet and outlet configurations, affect efficiency and pressure capabilities. Third component is motor. The motor provides the necessary mechanical energy to rotate the impeller. It can be electric, hydraulic, or pneumatic. Proper motor selection ensures that the blower operates within its specified parameters. So going back to the classification of blowers, centrifugal and positive displacement, from this slide, there are many components mentioned. However, I only focus on the three main components of the blowers common to both classification. Performance characteristics include pressure flow characteristics, operating point, surge and choke, turn down ratio. So there are 4 performance characteristics. So for pressure flow characteristics, understanding how a blower's pressure and flow rate change with varying operating conditions is crucial. Blower performance curves illustrate these characteristics, helping select the right blower for a specific application. Second characteristic is the operating point. The operating point on a blower's performance curve is where it operates most efficiently. Proper system design ensures the blower operates close to this point for optimal performance. Third characteristic is the surge and choke. Blowers have operational limits known as the surge and choke points. Surge occurs when flow is reduced too much, causing pressure fluctuations and damage. Choke, on the other hand, happens when the blower cannot deliver more flow despite higher speed, risking overheating. Another characteristic is the turn-down ratio. This indicates a blower's ability to operate efficiently over a range of flow rates. A higher turn-down ratio is desirable for versatility. So this slide will discuss about the operation procedure of blowers. First procedure is the startup procedure. Before starting the blower, ensure that all safety precautions are in place, including proper guarding and personal protective equipment. Verify that the blower is securely mounted or anchored to prevent vibrations. Then check also the lubrication system to ensure it is functioning correctly. Then second procedure is motor start. Turn on the blower's electric motor or power source. Then observe the motor startup process to ensure it operates smoothly without unusual noises or vibrations. Third procedure is the gradual speed increase. Gradually increase the blower speed to the desired operating level. Avoid abrupt changes to prevent system shocks. Then monitor the blower's performance during the speed ramp up process. Fourth procedure is the monitoring and adjustments. Continuously monitor the blower's vital parameters such as flow rate and pressure. Be prepared to adjust the blower speed or settings to maintain the required output. Fifth procedure is the shutdown procedure. To shut down the blower, reduce the speed gradually to avoid sudden pressure fluctuations. Then turn off the electric motor or power source. Then allow the blower to come to a complete stop. Sixth procedure is to have irregular maintenance. Implement a routine maintenance schedule to inspect and lubricate the blower components as needed. Check also for signs of wear, such as worn belts or damaged impellers, and replace them promptly. Seventh procedure is the safety precaution. We must also ensure that safety guards and protective measures are in place to prevent accidents or contact with moving parts. Comply with safety guidelines and use appropriate PPE when working with blowers. Eighth operation procedure for blower is the energy efficiency. Optimize blower operation by adjusting the speed and airflow to match the actual requirements of the system. Use control system or variable frequency drives to enhance energy efficiency and reduce operational costs. Ninth procedure is troubleshooting. If the blower exhibits abnormal behavior or performance issues, conduct a thorough inspection. Identify and address any problems promptly to prevent damage and maintain efficiency. Moving on to the third fluid machinery classification, which is the air compressor. It is a device that compress air or gases to increase their pressure. They are essential in applications like powering pneumatic tools, providing compressed air for industrial processes, and enabling efficient energy storage. This classification reflects, so in here, in this slide, it also shows the classification of air compressors. Air compressors also have classifications, just like fans and blowers. So, it is classified into reciprocating compressor and rotary air compressor, and centrifugal air compressor also. For the reciprocating compressor, it uses a piston cylinder mechanism to compress air through reciprocating motion. These are commonly employed in smaller scale applications where intermittent high pressure is required, such as in automotive workshops. Second type of air compressor is the rotary air compressor. It employs rotating elements such as screws or vanes to compress air. It is suited for continuous duty applications requiring a consistent flow of compressed air, such as industrial manufacturing and pneumatic tools. Third classification of air compressor is the centrifugal air compressor. It uses high-speed impellers to accelerate and compress air. It is ideal for applications needing high flow rates and relatively lower pressure ratios, including HVAC systems and some industrial processes. So, air compressors are devices that increase the pressure of air gases. And in this slide, we will discuss also the components of the said device or classification of the fluid machinery. First is the compressor housing. This encloses the compression chamber and it directs the airflow and maintains pressure. Second is the compression chamber. It is where air or gas is compressed. It contains rotating elements or pistons that perform compression. Third component is the compressing element. The compressing element, such as piston, rotor, or impeller, is responsible for reducing the volume of air, thus increasing its pressure. And then the design and condition of the compressing element directly affect the compressor's efficiency and performance. Fourth component is the motor or engine. The motor or engine provides the necessary mechanical energy for compression. It can be electric or internal combustion based. Fifth is valves. Compressors often have intake and discharge valves to control the flow of air in and out of the compression chamber. Proper valve design and maintenance are crucial for efficient operation. Cooling and lubrication systems is the sixth component. Air compressors require cooling to manage heat generated during compression and lubrication to reduce wear and friction in moving parts. Cooling and lubrication systems vary based on compressor type and size. For the performance characteristic of the air compressor, it includes pressure ratio, capacity, efficiency, power consumption, compression method, discharge temperature, oil-free or lubricated, noise level, maintenance requirements, duty cycle, and duty cycle. So, pressure ratio or compression ratio of the air compressor is the ratio of the outlet pressure into the inlet pressure. It indicates how much the pressure can increase the pressure of the air or gas, and higher pressure ratios typically require multi-stage compressors. Second characteristic is capacity or flow rate. It refers to the volume of air or gas that an air compressor can deliver per unit of time. It is often measured in cubic feet per minute. So, their capacity requirement depend on the application. Efficiency. Compressor efficiency measures how effectively the compressor converts the supplied power into compressed air. It is essential for minimizing energy consumption and operating costs. It can be affected also by factors like internal losses and mechanical friction. Fourth characteristic is power consumption. This refers to the amount of electrical or mechanical power required to operate the compressor. Fifth is the compression method. Compressors can be categorized based on their compression method, such as reciprocating, rotary screw, or centrifugal, as mentioned earlier, the three classification of air compressors. So, each method has its advantages and disadvantages in terms of efficiency, capacity, and pressure range. The sixth characteristic is the discharge temperature. It is the temperature of the compressed air or gas at the compressor outlet, to which a critical factor also. High discharge temperatures can lead to issues like moisture condensation and reduced equipment lifespan. Seventh characteristic is oil-free or lubricated. Compressors can be classified as oil-free or lubricated. They are used in applications where contamination by lubricating oil is a concern, such as food and pharmaceutical industries. Eighth characteristic is the noise level. It is an important consideration, also especially for compressors used in residential or noise-sensitive environments. Ninth is the maintenance requirements. Understanding the maintenance needs of the compressor is essential for ensuring its long-term reliability. Regular maintenance can extend the lifespan and maintain optimal performance. 10th characteristic is duty cycle. It indicates how long a compressor can operate continuously without overheating. It is important for applications with continuous air demand. So, this slide will present the procedures of air compressor. The same with the other classification of fluid machinery. The first procedure is start-up procedure. Ensure that the air compressor is correctly installed, secured, and adequately grounded. Verify that all safety measures and protective devices are in place. Turn on the compressor's power source, such as an electric motor or engine. Second procedure is the pressure adjustment. Set the desired pressure level and the compressor's pressure regulator or control panel. Then allow the compressor to build up pressure gradually to the specified level. Third is monitoring. Continuously monitor the compressor's essential parameters like pressure, temperature, and motor performance. Also, be alert for any unusual sounds or vibrations that may indicate issues. Fourth is the monitoring and adjustment. To shut down the air compressor, reduce the pressure gradually to avoid abrupt pressure drops. Turn off the compressor's power source and allow it to come to a complete stop. Release any trapped air to pressure in the system before maintenance. Fourth procedure rather is shutdown procedure. Sorry for the typographical error. So fifth is the regular maintenance. Implement a routine maintenance schedule to inspect and lubricate compressor components as per the manufacturer's recommendations. So replace also the air filter and oil as needed and keep the compressor area clean to prevent overheating. Sixth is the safety precaution. Then seventh is oil check if applicable. If the compressor is oil lubricated, monitor oil levels and quality regularly. Maintain proper oil levels and replace oil filters as recommended by the manufacturer. Eighth is drain moisture. Depending on the compressor type, regularly drain any accumulated moisture from the air receiver or compressor tank. This prevents moisture-related issues like corrosion and contamination. Ninth procedure is the cooling system if applicable. If the compressor has a cooling system, monitor it for proper operation and cleanliness. Then ensure adequate airflow for efficient cooling. 10th is the energy efficiency. Optimize compressor operation by adjusting pressure settings to match actual requirements. Use control systems such as unloaders or variable frequency drives or VFDs to reduce energy consumption during low demand periods. Lastly is the emergency shutdown procedure. Train your personnel on if you are operating an air compressor and issue with air compressors. Train personnel on emergency shutdown procedures in case of critical issues or safety concerns. Then ensure that emergency stop buttons and procedures are clearly marked and easily accessible. The fourth classification of fluid machinery is pump. Pumps are fluid machineries used to transport liquids from one place to another. They increase the pressure and velocity of the fluid, allowing it to overcome resistance in pipes or other components. Pumps are used in a wide range of applications, including water supply, wastewater treatment, and chemical processing. Pumps are also classified into different types based on their working principle and application. These classifications address the diverse requirement of applications such as water supply, wastewater treatment, and chemical processing as mentioned earlier from the previous slide. So the first classification is the centrifugal pump. It uses an impeller to impart kinetic energy to the fluid, creating a flow. This one on the right side. Next is the positive displacement pump. It drops and moves a fixed volume of fluid per cycle, suited for handling viscous fluids, slurries, and applications where precise flow control is needed, such as oil transfer and chemical processing. So this is positive displacement pumps. Third classification of pump is the axial flow pump. It moves fluid parallel to the pump shaft and are used for high flow, low pressure applications such as irrigation and flood control. Shown in the right side of our slide, this slide, is the axial flow pump and its component. The blade of the impeller, the guide vane impeller. So here are the basic components of pumps: impeller or rotor, casing, inlet and outlet ports, and drive mechanism. So I have already discussed about impeller or rotor, casing and inlet and outlet ports earlier, but in here this is the component of pump. So drive mechanism, pumps are driven by electric motor, engine, or other power sources. Performance characteristics include capacity, just like with the other classification. It includes capacity or flow rate. For pump, one characteristic is head or pressure head. It is the measure of the pressure that a pump can develop to lift or push liquid. It is often expressed in feet or meters of liquid column. Head determines the pump's ability to overcome resistance in pipes and deliver liquid to its destination. So third is efficiency, fourth is power consumption, 5 is the cavitation resistance. It occurs when the pressure in the pump drops below the vapor pressure of the liquid, forming vapor bubbles that can damage the pump components. Therefore, pumps should be designed to resist cavitation to ensure long-term reliability. Another characteristic is the net positive suction head or NPSH requirement. NPSH or net positive suction head requirement represents the minimum pressure required at the pump's inlet to prevent cavitation. It is crucial for selecting the appropriate pump and ensuring smooth operation. Seventh characteristic is the pump type and design. So I've already mentioned earlier the three of pump. Then material compatibility. So pump materials must be compatible with the liquid being pumped to resist corrosion and maintain performance. Ninth is the maintenance requirements. So maintenance. 10th is duty cycle. Lastly, the last slide for pump, last information for pump is the operation procedure. So same with other machineries. The first procedure is startup procedure. Second is prime the pump if required. For some pump types like centrifugal pumps, priming is necessary to remove air from the suction line and fill it with the pump fluid. Third is the motor start. Fourth procedure is monitoring. Fifth is flow control. Adjust flow control valves or throttling devices to achieve the desired flow rate and pressure. Ensure that the pump operates within its specified operating range. Sixth is shutdown procedure. Seventh, regular maintenance. Eighth is safety precautions. 9 is seal and bearing checks. Inspect seals and bearings for leaks, wear, or damage. Properly lubricate bearings as per the manufacturer's instructions. 10th procedure is the alignment and vibration monitoring. Regularly check the pump's alignment and monitor vibration levels. Misalignment and excessive vibrations can lead to premature wear and pump failure. Last operation procedure for pump is the emergency shutdown procedure. Lastly, is turbine. This is the last classification of fluid machinery. These are fluid machineries that designed to extract energy from a moving fluid and convert it into mechanical or electrical energy. They are widely used in power generations such as steam turbines in power plants, wind turbines for renewable energy, and aircraft engines for propulsion. So, turbines are also classified into 3 classifications or types. First is steam turbines. They use high pressure steam to rotate a series of blades on a rotor, which in turn drives a generator or mechanical equipment. So gas turbines operate the Brayton cycle utilizing high-speed rotation of an axial or radial compressor, combustion of fuel, and expansion through a turbine to produce mechanical power. It is commonly used in aviation, power plants, and industrial machinery. Hydraulic turbine. There are 4 classifications there. Third classification is hydraulic, then the last one is the wind turbine. For hydraulic turbine, it harnesses the kinetic and potential energy of flowing water to drive a rotor and generate mechanical power. These are employed in hydropower plants for electricity generation and in various industrial water management systems. The last classification of turbine is the wind turbine, which its function is to convert the kinetic energy of wind into electrical power for power generation. Then they provide clean, renewable energy and come in various sizes, from residential to utility scale, contributing to a sustainable future. So, as discussed earlier about the classification of turbines, as you can see at the right side of each slide, I have presented figures of each types of turbines, which shows the components as well. So the basic components or main components of turbines are runner or rotor. Second is housing or casing. Third is shaft and bearings. Fourth is nozzle or combustion chamber. So these are the 4 basic components of turbines. Runner or rotor is the central component that interacts with the fluid flow. It has blades designed to capture the fluid's kinetic energy. So housing or casing, it houses the runner and the fluid flow path. Next is the shaft and bearings. Then fourth, nozzle or combustion chamber. It controls the flow and expansion of the working fluid, while combustion chamber, nozzle control the flow and expansion of the working fluid, while combustion chambers in gas turbines facilitate fuel combustion. The proper design ensures efficient energy transfer and combustion. So, performance characteristic. So, one characteristic is the energy conversion efficiency, or known as flow rate sa turbine nga term. It measures how effectively the turbine converts the kinetic energy of fluid into mechanical or electrical energy. Power output is the second characteristic. It represents the rate at which turbine produces mechanical or electrical energy. Third is the rotational speed. It refers to the speed at which the turbine rotor or blades rotate. Fourth is the pressure drop across the turbine or turbine. Pressure drop indicates the change in fluid pressure as it passes through the turbine or turbine. Specific speed is a dimensionless number that characterizes the turbine's design and performance. It helps engineers compare different turbine designs and predict their behavior under varying conditions. 6 is flow rate or mass flow. Mass flow. It represents the amount of fluid that turbine can process per unit of time. 7th is the material durability. 8 is the operating range. 9th is control and regulation. 10 is the start up and shut down procedure. Turbines may have specific procedures for safely starting up and shutting down to prevent damage and ensure safe operation. For turbine, this is the last information that I will provide, which is the operation procedure. First procedure is startup procedure. Then second is the rotor alignment if required. Align the rotor blades with the direction of the fluid flow to optimize energy capture. Third is the control system activation. We must activate the turbine's control system to monitor and adjust operating parameters. Fourth is the gradual speed increase. Fifth is monitoring and adjustments. Sixth is the shutdown procedure. Then regular maintenance. 8 safety precautions. 9th efficiency optimization. 10th is the environmental consideration. So we must be mindful of the turbine's impact on the environment, including wildlife and water flow. Thus, implementing mitigation is needed. Mitigation measure is needed or necessary to minimize this ecological disruption. Load changes, if applicable. Some turbines may need to handle load changes or variations in fluid flow. So we must also adjust settings and controls to accommodate these changes without compromising efficiency or safety. 12 procedure is the emergency shutdown procedure. So in conclusion, fluid machineries including fans, blowers, pumps, air compressors, and turbines play integral roles in various industries. These machineries are the backbones behind various industries, ensuring efficient fluid handling, energy conversion, and power generation. We have explored the classification and specific purposes of each type of fluid machinery. Second is we have also discussed the essential components, performance characteristics, and operation procedures that engineers must consider when selecting, operating, and maintaining these machines. Lastly, or additionally, we have also highlighted the importance of safety precautions and environmental considerations. Our understanding of these fundamentals equips us to tackle real-world challenges and contribute to innovation in mechanical engineering. This knowledge will undoubtedly guide us as we embark on our professional journey in this dynamic field. Thank you for learning with me during the exploration of fluid machineries. God bless.